And I think that we should be live. Let's go ahead and share out the stream, and then we'll be ready to get started with this Good Friday morning. Also doing a quick spider check to make sure there's none around me. Had to kill a few this morning. But I think I'm good now. Ooh, it looks like they changed mobile update. Okay, how do I... There it is. Share this with Twitter. Share this with Slack. All right, perfect. But this is an interesting new interface that I could see on my phone as a streamer. An activity feed and a stream chat. And perfect, that's a way for me to know that it's working. Miguel, good morning. Welcome. Okay, so let's get ourselves set up and going here. All right, so we're currently at implicit deref coercions with functions and methods. Let's go to it. All right. Deref coercion is a convenience that Rust performs on arguments to functions and methods. Deref coercion converts a reference to a type that implements deref into a reference to a type that deref can convert the original type to. Deref coercion happens automatically when we pass a reference to a particular type's value as an argument to a function or method that doesn't match the parameter's type in the function or method definition. A sequence of calls to the deref method converts the type we provide into the type the parameter needs. So if we remember last time, we were basically creating our own version of box, which allowed us to dereference our box. Stacking, good morning. You're making your coffee, don't ask anything intelligent yet. All right, we'll wait until you get your coffee. Deref coercion was added to Rust so that programmers writing function and method calls don't need to add as many explicit references and dereferences with the ampersand and star. The deref coercion feature also lets us write more code that can work for either references or smart pointers. To see deref coercion in action, let's use the myboxt type we defined in listing 1518, as well as the implementation of deref we added in listing 1510. Listing 1511 shows the definition of a function that has a string slice parameter. All right, so function hello, it takes in a name, which is a reference to a string or a str, and then we do print line, hello, and then the name. So I think that is something we've noticed before, is that when we do print, we don't have to dereference because it sort of auto figures that out. We can call the hello function with a string slice as an argument, such as hello Rust, for example. Deref coercion makes it possible to call hello with a reference to a value of type mybox string, as shown in listing 1512. So function main, let m equals mybox new string from Rust, hello, and a reference to m. Interesting. So instead of like passing m there, we just pass a reference in. Here we're calling the hello function with the argument reference to m, which is a reference to a mybox string value. Because we implemented the deref trait on myboxt in listing 1510, Rust can turn reference to mybox string into reference string by calling deref. The standard library provides an implementation of deref on string that returns a string slice, and this is in the API documentation for deref. Rust calls deref again to turn the string into a str, which matches the hello function's definition. So basically, it's constantly auto derefing and auto starring, auto starring deref, and if it detects a reference. I got my coffee now. I'm no longer rusty. Oh, that's perfect. But isn't your plan for the next day or two to just accumulate more rust on you? I don't know. I think that was a worse pun. But I think today is the day you're gonna get 8+ hours of awesome dev and learning work with Rust, right? If Rust didn't implement deref coercion, we would have to write the code in listing 1513 instead of the code in listing 1512 to call hello with a value type of &myBoxString. You made it to chapter 4.3 yesterday. Oh, well then so chapter 12 is pretty much when, as far as like my rusty friends that actually have access to physically, and I've been chatting with them, and they said like once you reach chapter 12, like that's it. Now we're talking about higher level concepts that you don't use quite as often in programs. So it's really awesome we made it to 4.3. So let m equals mybox new string from this hello. So we're creating a reference, we're using parameters to wrap it, and then we're wrapping the deref of m, which gets out the string, and then we're referencing that and taking the full string slice from it, which is from the beginning to end. That is, I'm glad we don't have to write this code. This would suck. The parenthesis star m dereferences the mybox string into a string. Then the ampersand and the square brackets with the ellipses, the dot dots, take a string slice of the string that is equal to the whole string to match the signature of hello. The code without deref coercions is harder to read, write, and understand with all these symbols involved. Deref coercion allows Rust to handle these conversions for us automatically. When the deref trait is defined for the types involved, Rust will analyze the types and use deref as many times as necessary to get a reference to match the parameter's type. The number of times that deref needs to be inserted is resolved at compile time, so there is no runtime penalty for taking advantage of deref coercion. And I think we ran into one time where we had to do two derefs ourselves with like star, and that was a little bit annoying. I think that was back in the temperature calculator conversion thing. How deref coercion interacts with mutability. Similar to how you use the deref trait to override the star operator on immutable references, you can use the deref mute trait to override the star operator on mutable references. Rust does deref coercion when it finds types and trait implementations in 3 cases. From $t to $u, so these are just 2 different types, when t deref target equals u. Okay, so basically when the deref trait has been added to a type in which it knows that the target is u, it could then, and it's compatible, it will then auto cast. From a mutable reference of type t to mutable reference type u, when the type has the deref mute target set. From reference to mutable reference to type t to reference to U when the generic type has the trait deref set on it with a target of the U type. The first two cases are the exact same except for mutability. The first case states that if you have a reference to generic type T and T implements deref to some type U, you can get a reference to generic type U transparently. The second case states that the same deref coercion happens for mutable references. The third case is trickier. Rust will also coerce a mutable reference to an immutable one, but the reverse is not possible. Immutable references will never coerce to mutable references. So mutable references will never coerce to immutable reference. Immutable will never coerce to mutable. Okay, got it. Because of the borrowing rules, if you have a mutable reference, that mutable reference must be the only reference to that data. Otherwise, the program wouldn't compile. Converting one mutable reference to one immutable reference will never break the borrowing rules. Converting an immutable reference to a mutable reference would require that there is only one immutable reference to that data, and the borrowing rules don't guarantee that. Therefore, Rust cannot make the assumption that converting an immutable reference to a mutable reference is possible. Which, I mean, it makes sense. Running code on cleanup with a drop trait. The second trait important to the smart pointer pattern is drop, which lets you customize what happens when a value is about to go out of scope. You can provide an implementation for the drop trait on any type, and the code you specify can be used to release resources like files or network connections. We're introducing drop in the context of smart pointers because the functionality of the drop trait is almost always used when implementing a smart pointer. For example, box of generic type T customizes drop to deallocate the space on the heap that the box points to. In some languages, the programmer must call to free memory or resources every time they finish using an instance of a smart pointer. If they forget, the system might become overloaded and crash. Basically, they get memory leaks. In Rust, you can specify that a particular bit of code will be run whenever a value goes out of scope, and the compiler will insert this code automatically. As a result, you don't need to be careful about placing cleanup code everywhere in a program that an instance of a particular type is finished with. You still won't leak resources. Specify the code to run when a value goes out of scope by implementing the drop trait. The drop trait requires you to implement one method named drop that takes a mutable reference to self. To see when Rust calls drop, let's implement drop with a print line statement for now. So listing 1514 shows a custom smart pointer struct whose only custom functionality is that it will print dropping custom smart pointer. When the instance goes out of scope, the example demonstrates when Rust runs the drop function, which my guess is twice if we implement it in main, right? So struct custom smart pointer, data string, implement drop for custom smart pointer. So let's actually do this for our my box, and we'll use that. All right, so cd mine Rust chapter, was it 15? Yeah. cd into boxes, open up code here. You're overwriting drop, so I doubt it will go called twice since that's a double free error. Yeah, that makes sense. It won't get called twice because if I gave ownership to another function, that Well, what's left then is like just a shell. It will clean that up at the end. I basically wonder whether or not drop gets called on the shell being cleaned up. And let's see if I can explain what I mean. So in main, we have a new box here, B. And so we own this, main owns this box. So if we call a function now, so if we basically say print the box and we hand it B, we're giving ownership of this box over to this other function. So we're gonna say fn print the box. This takes in a box of type box. It's not going to return anything at all. It's just going to keep this ownership. And are you unhappy? Expected pattern found colon. Type error. Well, that's, I wanted you to be type box. Oh, wait, you're the type list. Expected pattern found colon. It needs to be an implementation. Did I completely forget how to do types with this? I didn't think I did. Because if we're implement. Well, the idea in here is that I would just dereference the my box and print it. And I would say, okay, print line, my box is, and we can have a dereference to a box like that. Expression, expected expression found end of file. You're not liking this. Function print the box B here. Did we like have halfway through like and then not finish something? I thought we had it working now. Let's actually go just see what the actual error, the real error is. So cargo run. Expected pattern, expected expression, could not compile boxes. So if I say something like box is going to be an I32, function question mark, okay. Is it like B? Oh, it doesn't like the word box. That's interesting. So it doesn't like box, the word box. But if I use B, everything's fine. Right, mismatch types. This is a list. Type list cannot be dereferenced. Oh, is it auto dereferencing here? Expected enum list found struct standard boxed box. Right, I don't want the actual box. I want this thing. That list equals const. No, I want my box. My box is a my box. Okay. I'm gonna hand it my box. And this is a my box type. I forgot that I had multiple types here. Okay, so function does not implement that. That's fine. We're going to dereference it here. Expected enum list found my box. We're going to put in, wait. mybox expected enum list found structure mybox. Right, you're a mybox type. You are a B. Wrong number of type arguments, expected 1, found 0. Expected 1 type argument. Oh, do I have to tell mybox which type it is? Do I have to say like, okay, mybox, this is gonna be type I32. Oh, then it works. Otherwise, I would need to make this as a generic. That's actually really interesting. Okay. All right, so let's run this just to make sure it's working. And it is. Let's now go implement drop for here. So we have implement dereference, and now we can implement probably T drop for mybox T type target equals. So Danny yesterday on the stream in YouTube commented saying that he prefers not to use target equals T like this, but rather grab it from self, I think. Although I'm not sure how to grab that anymore. If we go over to my YouTube channel, we can take a look at the comment. Here it is. All right, I prefer to use the self type when the trait specifies it. If you look at the source for the trait, you can see they specified the return as self target. It is a way for them to further specify how a type is being used in the function parameters or returns, and a way the trait can allow you to use a generic to do it. Brookception, yes, I know. All right, so here's what it is. So standard ops deref, struct mybox, type, so it's a tuple, implement t deref for my box, type target. Okay, so he still does this. Function deref type. So he's returning this self target in here. Oh, so that's what he's doing. So function deref right here. This is where he's doing self. Then we take the self : target. So let's try that here. So target is still going to be t. We're going to have a function, and what are we calling this? A function drop. We need to take in a reference to self, and according to this, do we need to return anything? Okay, no. So drop doesn't return anything, so we don't need to do that. The book doesn't mention self a lot. No, it doesn't seem to. It's mostly here for us to sort of figure it out a little bit on our own, unless they're going to talk about it a little bit later. So function drop, so it takes a mutable reference to self. That's interesting. Then in here, we're just simply going to print line dropping this smart pointer. So print line dropping the smart pointer mybox. Self is kind of crazy concept for new programmers. When you think about it, they might avoid it. That's true. And self.data. Well, wait, they're calling it self.data because that's in there. We want self dot self.0. And we kind of want a reference to self.0. Just lowercase self, but yeah, maybe later. Where did I... Oh, just the lowercase self. But yeah, maybe later. Well, let's... I hope that they do. All right, so what are you upset about right now? Target is not a member of trait drop, not a Oh, you're correct. We don't need target at all. And what are you upset about? T doesn't implement standard format display. T cannot be formatted. Oh, right, because it's a box. Is it this or is it the dereference that I need? Type T cannot be dereferenced. Oh, so I'm thinking right now, maybe not necessarily printing this out like that. We'll just do dropping the MyBox smart pointer because that's kind of all we want to do right now. And so we're going to see, okay, this comes in, prints it out, and then should be, we're expecting it to print out right here. And then again, probably not right here when that goes out of scope. Oh, but it does happen twice. Dropping a smart pointer, my box. Dropping a smart pointer, my box. That is actually really interesting. So it does happen twice. First time, this goes, we give ownership of my box over to print the box. Print the box uses it and then goes out of scope. So my box, which is in B right now, gets removed from, I guess it's going to be removed from the stack and removed from the heap because that's sort of where it's being carried. Is it being stored in the heap at all? In my box, it's just a tuple type. Actually, it's not necessarily doing anything crazy here. I think I32 is a problem here since it's a copy, not a clone. Oh, so maybe a string. Make this a string. So I could actually just create a new one. I'll take a look. My string box equals my box new. That might also copy. What if I do this? Let my string box. So since it's a copy, we technically do have two copies to destroy. You're right about that. I forgot. I didn't think about that. Okay, so how about a other string box equals my box new, and in this case we'll do string new and then hello. I'll just do hello, and we'll pass this one into here, my other string box. This of course should work with that. We'll dereference and print it out. This function takes 0 parameters, but 1 parameter is supplied. My box new. Wait. Oh, string from. Okay, so let's try this. And this is a string that we have in there instead of 3 of them. there's now 3 drops. That should be on the heap, so it shouldn't be doing copies, right? You're lost on this one? I'm a little bit lost on this one too. Okay, so let's figure this out. We're only calling print the box once. Oh, wait. We've implemented drop. Okay, hold on. I now know what's going on. Okay. We were thinking that this is the only time that it's dropping, except we're creating my boxes 3 times here. Because we're creating my boxes 3 times, there's going to be 3 drops because this gets created, it gets used by print line, and then it gets dropped. My string box gets used by print line and then gets dropped. My other string box gets ownership passed over to this function, then it gets dropped. And then we come back to here and whatever is remaining gets dropped. So the fact that we have 3 means that it's not passing in, dropping, and then dropping again. It's like those are specifically different ones. And I think the problem was because I didn't print out what the contents were, we couldn't figure out what it was. Can we have a print line message for which box is dropped, or is that too much? No, let's see if we can implement that. The only reason we didn't right away is because it was yelling at us about self and like not implementing print. So if we have something like this, then we want to put self.0 essentially. But what is this yelling about? That is impossible to read. Let's just get the real one. All right. T cannot be formatted with a default formatter. The trait standard format display is not implemented for generic type T. In format strings, you may be able to use the debug. Okay, so let's try the debug. Generic type T doesn't implement standard format debug. Okay, so same exact problem. Let's see what this says. Consider adding a where T standard format debug bound required by standard format debug. Okay. Now, can I dereference this? Type T cannot be dereferenced. Does this tell me that like maybe I can run a where? No, so it's not telling me I can do like a where dereferenced or anything. It just wants me to add a where T standard format debug. So where do I put that? I think in struct my box. Do I do it? Which one do I do it? Do I do it here? Do that. Parenthetical notation is only stable when used with the function family traits. Wrong number of type arguments. Expected node type arguments. Type annotations needed, cannot infer type for T. Okay, so where, if I can't put where here, it's an implementation, right? I think you need to do an implementation for standard format display. It's also a generic. No, it's the wrong place. And Catford, welcome to the stream. Good morning. All right, so it's in the wrong place. We need to go find out where to put it in the correct place. So it's going to be Rust generic where T. Oh, it didn't take me to the right place. All right, let's do Rust by example. Okay, so here's these, but we need the where. Ooh, Miguel, you gave me standard trait format display. Implement format display for point. Function format, self, function mutable format, formatter. Well, but if it's generic type T, we probably just want to make sure that we're storing the right one. Because I think what we really want to do is we basically just don't want to store T unless that T has the type. I think it's something like in that function test T, where T-bug. Oh, so it's afterwards. So instead of here, we would put it here. T doesn't implement standard format debug. T cannot be formatted with debug because it doesn't implement standard format debug. Help, consider adding a where T standard format debug bound. So it didn't like that either. This where doesn't seem to be. Oh, like where T colon D. Well, it's like this where T has standard debug. But of course, now it's saying it's not there, which means that it didn't actually work properly. I mean, can I just say that we derive the debug off of this? No, because it's generic, so we need to limit the generics. All right, where are we going to get the wheres? Example generics where maybe it can help. All right, let's take a look. All right, so implement these. Expressing bounds with a where clause. Implement blot trait where. Oh, so we don't put it. Use standard format debug trait. Print an option function. Print an option self. Implement generic type print an option for T where. Oh, so we don't put it. We don't put it here. We put it in down here. So implement T drop for my box T where the requirement T standard format debug is added only by the drop implementation. So everywhere else too. The requirement T standard format debug. Well, I added everybody else. let's run the real one and see if we get any better error messages out of it. Okay, so the requirement T standard format debug is added only by the drop implementation. Implement T drop from my box where T standard format debug. Function drop mute self. Okay. The same requirement must be part of the struct enum definition. Struct my box TT. Okay. Add this into the struct declaration, struct my box T colon. Okay, so, and then we have the standard format display debug. So you're suggesting we move that. So struct my box generic T, and then this will, I guess it won't be where. It's T, which has standard format debug, and then T here. So we're down to this. Type T cannot be dereferenced. Okay, so back to you. If I do that, okay, no error messages. Thank you, Catfert. Let's see if this works. So cargo run. All right, dropping the smart. So it does. So perfect. Catfert, that was super helpful. So dropping the smart pointer, my box, and this was just the hello. So if we take a look, this was this one first. Notice that it's the last one created. So come here, my box creates my box, creates my string box, my other string box. It prints my box, it prints my string box. Then we give ownership to the function print the box, my other string box. That then prints it right here. My box is hello. But then it drops it because that function is done. Then the main function is done and it sort of unwinds in reverse order that it created them. So then it's dropping a smart pointer hello world, which is this one, and then the 55, which is this one. So it is only running them once. So even if I did, so let's say we now passed in my box over again. So if let's comment you out. Let's do the original one again, which was, this is an I32. And we're gonna call print the box, and we're gonna pass in my box. Damn, I'll have to go watch the vid. You got a phone call. Oh yeah, too bad. We figured it out with thanks to Catvert. All right, so let's see. We should still only get 2 drops. But now 55 should be the first one. Yeah, so 55 drops and then hello world drops. So it isn't copying, because if it was copying, it would have to drop both things, the one that it copied and also the one that it didn't copy. It didn't do that. I think also Miguel or Stacking, Miguel, was it you who showed us that we can do some interesting things with :P when printing. So print line my box is this. So if we create our box, we can also say this, print line memory location of my box is :P, and it'll be my box. And we want to do the exact same thing. Oh, yes. Okay, so print line, my box is, oh wait, why don't, the trait bound my box standard format pointer is not satisfied. It's not implemented for my box. Oh, we're gonna have to add that in there, aren't we? My box I32. Could we do it with the other one, my string box? I think I start, oh, the star, well, I could dereference it, yeah, with my box. So if I dereference this, then print the box inside of here. Actually, when it goes out of scope, drop, we can do P. The trait bound T. Oh, right. So now we're gonna have the exact same pointer where now we need to say like where T. Okay, so how do we do two of those? Because right now we have struct T standard format debug is the same thing as the debug. So instead of debug, we're just gonna do standard format pointer. Which of course, now we're gonna get these problems everywhere. So these could become pointer as well. And down here, okay. The trait bound integer pointer is not satisfied. Standard format pointer is not implemented for integers. So I'll just comment you out. Or wait, can I just do this on my string box? And then will you be happier? Probably not. I'll just not use you. I'll just use this stir. You don't exist anymore. Print the box. We're gonna pass in my string box, which you are now a stir. Are you a stir? New. I mean, yeah, you are. So print the box. We pass in my string box. Yeah, print the box. This. Okay, so the trait bound stir marker size is not satisfied. Stir does not have a constant size known at compile time. Help. The trait standard marker size is not implemented for string. The trait bound string standard format pointer is not satisfied. A reference to stir. I could try that. It shouldn't be. Because we don't know how big this is. I shouldn't have to say like reference to stir here because that's not really a type, is it? Or string is cheap. Actually, this did work. I put the reference on so you were correct. We put the reference to stir here in the print the box. There's no more red squigglies. So let's see if we can get these interesting memory locations printed out. All right, so memory location of my box is 0x, and then we'll just look at the last four, 0DDC, and then dropping a smart pointer from my box, 0x, 0DDC. So I guess what we could do this it's like it's not copying it over. It's the same address and memory that is being dropped and being used. I think that's the most important thing to think about here. My smoothie separated out, so not as fun to drink anymore. I'll have to wait until I can stir it later. But that was this is a fun sort of like way off the trail that we went. That was just for us to put this drop here. All right. The drop trait is included in the prelude, so we don't need to import it. We implement the drop trait on custom smart pointer and provide an implementation for the drop method that calls printline. The body of the drop function is where you would place any logic that you wanted to run when an instance of your type goes out of scope. We're printing some text here to demonstrate when Rust will call drop. They should make a little code like this in a book to show lifetimes. It would come in handy. I think they did a little bit later on, right? Or am I thinking about something else? I guess they showed a little tiny bit of code like that, but I think the big thing is, Miguel, you wrote the lifetimes thing, I believe. That's a really good resource. Good enough that I want to show that off here. I think it was in issues, lifetimes. Yeah, so this is a really awesome resource of the lifetimes. Which sort of like goes through of what's going on, with some awesome comments about even giving lifetimes types essentially. But let's continue. In main, we create 2 instances of custom smart pointer and then print custom smart pointers created. At the end of main, our instances of custom smart pointer will go out of scope, and Rust will call the code we put in the drop method, printing our final message. Note we didn't need to call the drop method explicitly. When we run this program, we'll see the following output. Custom smart pointers created, dropping custom smart pointer with data other stuff, dropping custom smart pointer with data my stuff. Rust automatically called drop for us when our instances went out of scope, calling the code we specified. Variables are dropped in a reverse order of their creation, so D was dropped before C. This example gives you a visual guide to how the drop method works. Usually you would specify the cleanup code that needs to run rather than the print message. So by implementing this trait, we're not actually overwriting how drop is happening completely, right? Because that seems like it would be bad. Because like, let's think about this. If we're coming here, we're supposed to be dropping. We're supposed to be dropping this. So if we attempted to use it again, like just print the box twice. Like if we did this, it should now yell at us that we can't use moved things. Use the moved value, my string box value used after here. Value moved here, but the value used after move here. Okay, I wanted to make sure that it wasn't doing something like, oh yeah, we no longer drop that at all because you wrote your own. I should be getting a lifetime soon. Not sure what chapter. I can't remember exactly what chapter they're in either. Let's see. Dropping a value early with a standard mem drop. Unfortunately, it's not straightforward to disable the automatic drop functionality. Disabling drop isn't usually necessary. The whole point of the drop trait is that it's taken care of automatically. I just realized though that this is going to be decently long and I only have 5 minutes left. So I'm actually going to not go through this right now, and we'll just do this on Monday when we come back and continue on. So let's go ahead and get this all set up. So we'll open up code here and we'll update our README. You did have a question. You installed RLS, but it's installing it for every project I make. Is that normal, or did I butcher the install? So I didn't install RLS manually. What ended up happening was I installed Rust with Rust Up. It installed everything it needed to install. I didn't I didn't customize it. Then I opened up VS Code and it said, hey, there's a Rust tooling that I want that you need. Would you like me to install it? So I clicked that and then everything just died. And I had to force quit VS Code, and when it came back, it was all installed. It was all installed, and then everything was working. So it's driving you crazy. You have to install it again for every project. Interesting. Yeah, I don't think that it should happen. I mean, I think I have RLS installed. And specifically when I come into here and come into like one of these projects, it does say like, hey, I can't actually use this. And RLS is sitting here. So I just did let I let it run. Now, are you having like are you opening VS Code in the root of your Rust project where the cargo.toml is? Because maybe it's a problem. Maybe that's the problem. All right, so currently at here, and we'll get the URL. All right, so next time on Monday, we're going to go into dropping a value early with standard memory drop. That doesn't sound good. You can't even get RLS installed, so no idea. I'm just doing new cargo, new hello world, cd cargo, and code dot. Huh? Yeah, that should do it for you. Are you on the latest version of VS Code? Yeah, that's the only thing I can think of. Maybe going in and like removing Rust. Yeah, maybe removing the Rust RLS package and then like reinstalling it through this. But like it's definitely installed here. All right, so we're updating all of this. What did we get? We did custom trait to see when my box is dropped from memory. And we'll push this on up. Well, if it continues not working, I wouldn't worry too much about it. If you can get like the red squiggly lines and other things, I've noticed that those sometimes don't work. Like I'll get red squiggly lines when there's no actual error. Like I'll cargo run it and everything works just fine. So I don't know. Maybe it's because I'm running on Linux and things like the tooling is just almost there but not quite. Or maybe it's something else. We'll just have to nuke the install off this stream and try again. Yeah, that's the only thing I can suggest. All right, so we got our code updated. Everything should be up on GitHub now. We have all this code here in the Learning Rust repo. Specifically, today we worked on chapter 15 boxes, and we have links to where we're at in the book. I have links to here in the stream description and also in the YouTube video description if you're watching from there. Don't hesitate to try IntelliJ. So yeah, I heard that IntelliJ does have a new a new Rust plugin. This is the best configuration for programming with Rust I found. I haven't tried it too much. I tried a little, like, I installed a little tiny bit and I couldn't type until I did one of the keyboard shortcut commands. But that also might be a Linux problem. I think the tooling for everything is just a little bit new right now for everything Rust. But hopefully things will get better shortly, and we'll be able to program in all the places with Rust, whichever methods we want to. All right. What else do we have? I don't think I got everything. So if you like these videos, you want to be notified when I go live, then please subscribe to me. You can follow me here on Twitch. You can subscribe to my channel on YouTube, and you can also follow me on Twitter, where I usually tweet out when I'm about to go live. I was seeing they nuked the match again, trying to fix it in the 127.1 patch. So now we're getting 127.2. Yeah, no, they can't wait for NLL. That was an interesting thing that you sent, Stacking, about them saying that maybe they should have made it a blocker until NLL was done. But every language has some interesting parts that sort of has to go through in the growing years. But I'm looking forward to continuing to work with it and maybe not having code that is bug filled just because of accidents that we have, because the compiler can stop those things. All right. With that, I'm going to get on with the rest of my day. I hope that you all have a great Friday and a great rest of great weekend. And I don't advertise any streams on the weekends, but if I do, I put that out there on Twitter usually. No guarantees that I'll give like any heads up necessarily for it. But my next official stream will be Monday morning at 7 a.m. when I continue learning Rust. All right, have a great day and weekend, and I'll see you all next week.